Good morning, everyone. Welcome to the statics course. Today we are going to cover chapter 6.4. It's the method of sections. Before we start chapter 6.4, I'd like to make an announcement, which is a midterm exam 2. So we will have a midterm exam 2 on next day at 11 a.m. It will take around 1 hour and 30 minutes. The midterm exam 2 will cover 3 chapters: force system, resultant, equilibrium of rigid body, and chapter 6, structural analysis. So today's lecture and next class lecture, which is space thrust, that is the last chapter of this chapter 6. The midterm exam 2 is an open book exam. So as we did last week about the quiz, this will be the same format. So this one, the midterm exam 2, I will upload the questions on the Blackboard. So you can solve the problems and submit your handwritten solving process through the link. You may need the engineering calculator, and this is 20% of your final score. Okay. Let's move on. Today's chapter is 6.4, the method of sections. Today we have one learning course. Understand how to utilize the method of sections. What's the method of sections? Do you remember the last week we learned the method of joint? When we find whether the truss member is in tension or compression, we can use method of joint. So we can pick the joint and calculate the equilibrium equation, and then apply all the equation, find the unknown forces, internal forces. That's the method of joint. Today is a little bit different things, but this is very useful compared to the method of joint. Okay, so method of sections. Let's look at the method of sections. So if you look at this crane is consist of a number of truss. So this is kind of a very long trusses. Okay, but the question is, if we want to know whether in the middle of the truss, for example this one, whether this truss member is in tension or compression. How about this one? This one. It's really hard to find if we use the method of joint, because when we use the method of joint, we can pick the point from the end point, or here, here, right here. So we can start all the way and go up and down, up and down, up and down, and we can find where is this one, what is the tension or compression. This one takes very long time. Okay, so we want to identify whether in the middle of the truss, whether this section is in in tension or compression. We can identify the directional force correctly. Okay, so here we have a simple truss. The method of section is basically you have to make a cut. Okay, this is imaginary cut. If you look at the images here, we have a cutting line which is AA. So this is cut, this is also cut, and this is also cut. So basically, if we want to find the member CG, whether we don't know, but we can apply this method of section to figure out the internal force. This is the you have to memorize things. The first thing is so we know that each truss member there is an internal force or zero force member is fine. But if the member is in tension, which means there is a pulling, okay, you can see the left hand side, this is the tension, and right hand side is compression. So if the member is in tension, if you cut in the center, okay, you these members, then the rest of the two members, they are still in the tension. Okay, so again, the member was in tension, cut in half, and then, the rest of them, they are in tension with the same amount of the force. Here you can see the large number, uppercase T, this amount, the force amount is the same. How about the compression? Same. If the member was in compression, which means push forces at the joint, then if you cut in half, the two divided object, they are still in compressions with the same amount of force. So like I showed you before, let's say we cut, this is line AA, okay? We cut truss in half. Then, since the entire truss is in equilibrium, we can say that, okay, divided, cut this area is also in equilibrium. We can apply the three equations what we learned so far. We can apply these three equations to this object. How many unknown forces we have? We have three unknown forces here. Okay. The question is, okay, let me ask you, what is the fastest way? What is the fastest way to find the force in member F? If you think this structure is in equilibrium, what is the fastest way to find the GF? We have one external forces, which is pulling the downward, which is 1000 Newton downward forces, and there is no other external forces. In this case, we have to use the moment equation. So how to find the GF directly? If I were you, I will choose the moment at point C. If you find the moment at point C, this one create the what is that? Point one create rotations, and this one should be clockwise rotations, because that's how we can satisfy this equation. Sigma moment is equal to 0. So when you calculate the moment at point C, you can directly find the magnitude GF, as also you can find the direction of the GF. Right now, if you look at the direction of the GF, what this direction indicating? If you see that this force is toward joint, this force is toward the joint G, that means this one is in compressions. This one is in compression. Because if you look at the direction of the force, this force is pushing toward point G, okay? So this one is in. You can choose this side or this side. It's up to you, okay? You can decide to choose which side you have to use to solve the problem. If I were you, I will choose the side that has a less unknown forces. if you look at the right images, you can definitely realize that there are many forces are associated with the right-hand images. On the other hand, the left images does not have many unknown forces. So let's choose the left one. But the answer should be the same. When you calculate the 3 unknown forces here and the 3 unknown forces here, they are all the same magnitude. Okay? So there is a step to solve this problem. Cut the trust. You want to identify the members. Please cut the trust that cross the member you are interested in, and choose which side you're gonna use, left side or right side. It's up to you. And the third step is try to identify some support reactions and external loadings on the free equilibrium equations. Fourth step is again, you have to draw the free body diagram first, okay, and indicate which one is unknown forces, which one is known forces. When you calculate the cross-section area, here we have 3 unknown forces. We don't know the direction, which means we don't know whether these members are in tension or compressions. Then my suggestion is you can assume all the members are in tension. You can assume all the members are in tension. So when you're beginning the calculations, you can decide, okay, these members would be the tension. So you can decide the direction. But after your calculation, if you got a negative sign, negative value, then your assumption was wrong. So you can just switch the direction to the opposite. So it's not tension, it should be the compressions. Okay, so direction is not that important. You can change it later based on your investigation. The last step is the apply equilibrium equations. Like I showed you before, if you can use the moment equations and then the moment equation identify unknown forces directly, then just do it. So you can minimize you can reduce the number of unknown forces fastly. Okay. Useful. So first you have to look at the questions and problems and think about which point you can choose for calculating moment. Sigma moment is equal to 0 to identify one unknown forces directly.